Fundamental constants might not be constant after all. The very numbers that anchor physics, like the fine structure constant or the gravitational constant, could drift as the universe ages. A change, even tiny, would ripple through chemistry, stars, and technology in surprising ways. This exploration unpacks the hypothesis of variable physical laws, where it came from, what experiments and observations could reveal it, and how scientists separate real signals from noise. We'll travel from ancient speculations to modern data, looking at spectra from distant galaxies, atomic clocks on Earth and in space, and the cosmological clues that could prove or falsify drift. By the end, you'll see what counts as evidence, what current measurements say, and why the question matters for how we understand reality itself. Parameterizing constants. Parameterizing constants means expressing how fundamental constants might vary by encoding their values as functions of a dynamical field or of cosmological variables. The core idea is to work with dimensionless combinations, because only those can be observed to vary in a meaningful way. One uses a functional form that translates the evolution of an underlying field into a change in a constant, such as the fine structure constant alpha or the proton-to-electron mass ratio μ. This approach keeps units out of the picture and lets experiments constrain the parameters of the chosen model. In practice, researchers pick a convenient parameterization that ties a constant to a scalar field, to the scale factor, or to redshift, and then translate that into observable quantities. The result is a framework you can test against spectroscopic data, cosmic backgrounds, and molecular measurements. Common choices include linear, exponential, and power law mappings. Linear in field, C phi, is almost equal to C0, 1 plus kappa phi, for small phi. This form is simple and lets data constrain the combination kappa phi without committing to a runaway behavior. Exponential, C phi, equals C0 e caret psi phi, keeps C positive and is common when phi is a dilaton-like field. It can produce smooth variations over cosmic history. Power law and the scale factor, C A equals C0 a to the power of S, with S a dimensionless parameter that measures how quickly the constant drifts as the universe expands. Redshift-based parameterizations, delta C slash C0, Z, equals F, Z, and one often uses low-order expansions. For small changes, a linear in redshift form delta C slash C0, Z, is almost equal to SZ is a convenient toy. It captures the idea of a gradual trend without prescribing a rigid theory. Oscillatory forms, C, A, equals C0, 1 plus a cos, omega log A plus delta. This kind of pattern can arise when a light scalar field moves in a potential with periodic behavior, producing repeating variations as the universe evolves. Each choice emphasizes different physics and offers different handles on data. Concrete examples help connect the parameterization to measurements. The fine structure constant alpha can be modeled as alpha, phi, equals alpha 0 b underscore f, phi, where b underscore f, phi, is almost equal to 1 plus zeta underscore f, phi 0, for small changes, or more generally alpha equals alpha 0 e caret zeta phi. The proton-to-electron mass ratio μ can be treated similarly, with μ phi equals μ0 v underscore μ phi, and b underscore μ phi is almost equal to 1 plus eta phi 0 for small shifts, or μ equals μ0 e caret eta phi. This mapping makes it straightforward to translate a guess about phi's evolution into predictions for spectral lines in quasar spectra or molecular transitions in distant galaxies. Observables such as shifts in atomic or molecular lines, or distortions in the cosmic microwave background, can then constrain the dimensionless parameters zeta, eta, or the functional form of b underscore f and b underscore μ. The emphasis stays on dimensionless quantities so that the tests remain meaningful across different experimental setups. From a practical standpoint, choosing a parameterization involves balancing simplicity, physical plausibility, and data sensitivity. Use of dimensionless combinations avoids unit confusion and often clarifies degeneracies with other cosmological parameters. A simple linear in-field form is easy to fit but may miss long-term trends. An exponential or oscillatory form can capture more complex histories but introduces more parameters and potential overfitting. When analyzing data, Researchers typically test several parameterizations to see which, if any, are favored, and they report constraints on the corresponding dimensionless coefficients. The goal is to connect a plausible dynamical picture to concrete, testable predictions, keeping the parameterization transparent and interpretable so comparisons across experiments remain meaningful. Today we explored the provocative idea that some physical constants might not be constant after all. If constants like the fine structure constant or G can drift over cosmic time, the implications would ripple from atomic spectra to the growth of galaxies. We looked at how such variations could show up, tiny shifts in spectral lines, changes in reaction rates, or anomalies in clock measurements, and we reviewed the kinds of evidence and the tight constraints scientists have placed on them. Theories that allow changing constants often involve new fields or evolving landscapes of the laws themselves, while experiments and observations across cosmology, geology, and laboratory physics keep pushing the bounds. If you're a curious thinker, you might be wondering how stable the rules we trust are in daily life, or what it would mean for technology if constants could drift. The conversation invites us to rethink what constant really means and where our understanding might bend under new data. If this sparked questions or a fresh angle, drop a comment below and consider subscribing for more ideas at the edge of physics. In the next videos, we'll dive into how scientists test for variations with atomic clocks, spectra from distant quasars, and nuclear phenomena, plus the math behind the models that let constants change. We'll also look at what a confirmed variation would require for our theories and for everyday technology. Thanks for watching, and see you in the next video.